sort of remind you where we are. So we're on the 12th right now, so we just have a few days left when we come back. I'm pretty sure that we'll finish up chapter 7, but if we don't, we don't, that's fine. But I'm pretty sure that we will. But definitely we'll finish chapter 6. So you should be looking at the homework for chapter 6, and we might even get a little bit into chapter 7 today. So let's start now with Lenz's law. I sort of alluded to this with Lenz's law last time. We use Lenz's law to determine the direction of an induced current. In a loop. So remember last time we said that if you change the magnetic field, then it induces an electric field within this loop of wire. And in fact, that electric field is going to be perpendicular to the magnetic field because, well, let's go back to what we were talking about before. When we looked at these experiments that what's his face did, Michael Faraday did, we talked about the magnetic field that's changing, and then you have this loop of wire right here. The electric field is induced within this loop of wire, and it's perpendicular because our magnetic field is in this direction, and our electric field, let's see if our current is going in this direction, our electric field basically follows the same direction as the current. So our electric field is always going to be perpendicular to our magnetic field. We don't get into electromagnetic radiation in this class. It's sort of in the third semester of physics, which we don't offer. But if you ever take that class, you'll get into the electromagnetic fields. There's an electric field and a magnetic field that describes light, and those are perpendicular wave fronts, that the electric field is always perpendicular to the magnetic field. And we begin to see that here with Faraday's law and Lenz's law. Okay, so Lenz's law helps us to describe the direction of the induced current, this induced current which is caused by an induced electric field. And it says something like this, that an induced current has a direction such that the current opposes the change in the magnetic flux. I'm sorry, that the magnetic field due to the current opposes the change in the magnetic flux, or the B flux, that induces the current. That's a little wordy, and I'll go through some examples and show you exactly what that means. But we basically have two examples. One is opposition to pole movement, and then the other is opposition to flux change. So let's say, for example, I have a loop of wire. And then over here, I have a magnet. I have a magnet that has a north pole, and it has a south pole. And I'm going to move this magnet in this direction. So I'll move it with a certain velocity in that direction. Now the magnetic field, if I were to just draw the magnetic field of my magnet, it's going to be in that direction. And so the magnetic field that's induced in this loop of wire is going to be in this direction. So this will be my, I'll call this B induced. And so as a result of that, the current, you're not actually inducing a magnetic field, you're actually inducing a current or an electric field within that wire, but we can determine the direction of the current by looking at the induced magnetic field. So if I have a magnetic field that is in this direction, that means in this loop of wire, I have a current that is flowing in this direction. So if I think about this loop of wire, this is on the back side, this is on the front side. If my current is like this, then my magnetic field is like this. So this is a loop that we're looking at from this direction, and that current goes in this direction, causing an induced magnetic field to the right. But notice that the induced magnetic field is opposite the direction of the magnetic field of the magnet. So Lenz's law describes this, that the induced magnetic field will be opposite the direction of the changing magnetic flux. And so, similarly, if I have a coil of wire like this, and I have a magnet, say that looks like this, where I have, now I flip my magnet, so I have my north and my south pole, and I'm still moving it in a direction like this, then my magnetic field of this magnet is going to be in this direction, and so the induced magnetic field will be in this direction. And that's going to cause my current to go in the opposite direction, like that. I have this device that shows this. We have a piece of copper wire, or a piece of copper pipe. And in it we have a couple of pieces. Now copper, is it ferromagnetic or not ferromagnetic? Like if I have a magnet and I put it on copper, will it stick or not? Y'all know if copper's magnetic or not? Okay, it turns out that it's not, but I have a magnet here, and if I drop this down through the pipe, it just falls, right? This device actually is not magnetic. This is just a piece of metal. But this is magnetic. I can stick it to things. This is a magnet. So watch what happens here. Now, as it goes through the pipe, it has a magnetic field that is going in that direction. So the pipe will also have an induced magnetic field, which will be in which direction? Down or up? It's going to be up. And so you'll get an interaction of those two magnetic fields. You have the magnetic field of this magnet, which is traveling downward, and then you have the magnetic field that's induced by the copper pipe. Now, copper is not magnetic, so this isn't a magnetic field that's generated by some natural magnet, some permanent magnet. Instead, what's going to happen is as this magnet travels through the pipe, it will induce a current in the pipe that will generate a magnetic field that opposes the direction of the motion. Oh yeah, you got stuck. Well. Notice that it travels more slowly. The reason is because I get this induced current inside the copper pipe. Copper is quite a good conductor. And that induced current then generates a magnetic field. I'll pass this around so you can take a look at it. Don't shock yourself from the induced current in the copper pipe. Now you can also have opposition to pole movement, and don't sweat it if you're not getting this. I figure most of you aren't getting this right now, but we'll do some examples and I'll show you how to figure out the direction of the current and the direction of the induced magnetic field. You can also have opposition to flux change. The magnetic field due to the current that's your induced magnetic field, does not oppose the direction of the magnet. Necessarily. Now we do have that up here. We have that the magnetic field of the magnet is here, and the induced magnetic field is in the opposite direction. We saw that here, and then we also saw that here when our magnet is traveling in the same, or towards the coil of wire. But that's not necessarily true. The magnetic field of the coil can also be in the same direction as the magnetic field of the magnet. Because instead what Lenz's law is saying is that the induced B field opposes the change in the magnetic flux. With the operative word being change there, that we're instead looking at the change in the magnetic flux. So in this case, the magnet is moving to the left, and so this coil sort of wants to keep the status quo. And because the magnetic field is increasing as I move this magnet towards the coil, it's going to generate a magnetic field that's opposite the direction of the increasing magnetic field. And then likewise on the previous one, the magnetic field of the magnet is to the left. The magnetic field of the coil that's induced is opposing it, but only because the magnetic field is increasing. This magnet is approaching the coil, so I have an increasing magnetic field, and so I'm going to generate a magnetic field that's opposite the direction of the permanent magnetic field. So if I think about this, I can have basically 4 different scenarios. I can have a scenario where I have a coil like this, and I have an increasing magnetic field in this direction. That would mean that I'm taking a permanent magnet and moving it down in this direction. And then the coil is going to generate a magnetic field, or generate a current that will have a magnetic field in this direction. That's like one that we've already seen, one of those 2 scenarios. And in this case, my induced current that generates this magnetic field will be in this direction. Think about my right-hand rule. My current is in this direction, so my magnetic field that's induced is up. So my current is going to be in that direction. That will induce that magnetic field. I can also have a scenario, which we've already seen, where I have an increasing magnetic field in this direction. And as a result, I'm going to have my induced magnetic field in this direction. And let's see, that's going to be a current that is the opposite direction. So my current is going to be like that. So here, current in this direction, my magnetic field is down. My current flows like this. So these are like the 2 examples that we've already seen. But I can also have a situation where I have decreasing magnetic fields. So let's say I have a decreasing magnetic field in this direction. That would mean that I'd be pulling the magnet away, basically. So I would have a north pole, south pole with a velocity in that direction. Because as I move my magnet away, the magnetic field is going to be decreasing. Everybody with me so far? Let me step back through it, okay? It's kind of a complicated idea. My induced magnetic field is going to oppose the change of magnetic flux. If there's a change of magnetic flux, it's like this is going to step in to try to ameliorate or try to mediate or try to take away that change. It's going to oppose any change in magnetic flux. So for example here, if I have an increasing magnetic field in this direction, then the induced magnetic field is going to be the opposite direction. The induced magnetic field will be opposite the direction of an increasing magnetic flux. And so, for example, here I would get an increased magnetic field by taking a magnet like this and moving it in that direction. That would increase the magnetic field in this coil of wire. Similarly, over here, I would get an increase in the magnetic field by taking a magnet north-south like that and moving it in that direction. And because my increasing magnetic field is up, my induced magnetic field is going to be opposite that, but only because it's increasing. Now over here I have a decreasing magnetic field. I get a decreasing magnetic field because I take my magnet and I pull it away from the coil. So what is going to be the direction of the induced magnetic field in this case? Is it going to be up or is it going to be down? The induced magnetic field. What do y'all think? Down is right, because it wants to oppose any change in magnetic flux. So you imagine you have this magnet here, you have a certain magnetic flux around this coil, but then I start to take it away. And you can think of it as the coil saying, oh no, I don't want anything to change, although the coil doesn't really say anything, but I don't want anything to change, so now I'm going to generate a new magnetic field that will try to keep the status quo. So because this magnetic field is decreasing, I'm going to have an induced magnetic field that's in the same direction as the decreasing magnetic field. Well, let's see, that's going to be a current that is, what's that going to be? Into the phase, all right, it's down, so yeah, it's going to be like this. So on the outer part, that will look like that. Now I can have a similar situation where I have a decreasing magnetic field but upwards. That would be the scenario where I have a north-south magnet in this direction but traveling with a velocity away from the coil, causing the magnetic flux to decrease. And then my induced magnetic field will be in the same direction because it's decreasing as the changing magnetic flux. And then that would give me a current that would be in this direction. So those are really the only 4 scenarios that we can have. But in all of them, the induced magnetic field, which is caused by the induced current, which is caused by the induced electric field, is opposite the direction of the changing flux. So that's really the key that we need to understand with Lenz's law, that the changing magnetic, the induced magnetic field opposes any change in magnetic flux. And it's like it's going to step in and fill in where I'm losing flux. It does it here. We're having increasing magnetic flux. It puts it in the opposite direction, which returns it, sort of, or tries to return it back to that original state. Here, my increasing magnetic field is in this direction, so my induced is opposite that. And then, when my magnetic field is decreasing, pulling the magnet away, I get a decreasing magnetic field, so my induced is in the same direction as the magnetic field. And then here, decreasing in this direction, I get an induced in that direction. So I'm always going to oppose the direction of the magnetic flux. Thank you. So here, as this thing moves down through the pipe, you have a couple things going on. As it moves down, as this magnet moves down, the magnetic field on the bottom part is going to be upwards. The magnetic field on the top part is going to be downwards. And the net result of that is that it's going to interact with the magnetic field of the permanent magnet and cause it to slow down, that you'll actually get forces that will act between the different magnetic fields. Okay? Jesse?
As soon as you have like little rubber bits on your magnet, is that so it doesn't shatter when it hits the ground, or is it because impact to the magnet can alter its magnetic field? Because I heard about that.
Yeah, that is true. I think this is more just, they're pretty strong magnets. I don't think that they would be altered by hitting the ground. But you're right that if you have, especially a kind of a weak magnet, and you just bang it over and over, that can disrupt the magnetic field. It gets back to our magnetic domains. if you do get a very weak magnet, it can do so, but not so much weak. I don't know why. I think maybe it's to keep people from pinching themselves. Because you have two pieces. I think that's the mechanism. All right, so that's Lenz's law. We'll revisit that. We'll have some clicker questions, probably not today, maybe next time after the break, to sort of revisit Lenz's law as we prepare for the exam. Let's see, let's try a problem. You have some homework problems like this, and this will be akin sort of to what you'll have on the exam 4. I have a half loop. The half loop looks like this. You don't have it drawn, but I'm going to draw it for you. I have a battery attached to a loop of wire like this, and then there's a magnetic field which is out of the page, but that magnetic field changes with time. Remember, there are a couple different ways that we can induce currents. We can change the magnitude of the magnetic field with time. We can change the we can change the area of the loop, or we can change the angle of the loop, right? And what's the most common way to create an induced current in practice? We can change the magnitude of the magnetic field. That's what we're doing here. We can change the area of the loop, or we can change the angle between the loop and the magnetic field. Y'all remember the most common, like in generators and what? Right, the angle, right? This gets back to my EMF is equal to the negative of d phi dt, and that phi is the magnetic field times the area. It's actually the dot product, so it's BA d cosine theta, or BA cosine theta. All right, so here I want to know what is the induced EMF at t equal 10 seconds. Here's my magnetic field. I want to start with that basic definition of my induced EMF is equal to minus d phi dt. Let's see, I have some other properties of this, so let me go ahead and draw them here. The radius of this loop, which I'll need to know, is 0.2 meters. And the EMF of this is 2.0 volts. And the resistance I'm sorry, that's not the EMF. But the resistance of this is 2 ohms. The resistance is 2 ohms. And I want to know what EMF is produced in this loop. So I have, from Faraday's law, that the induced EMF is minus d phi dt. And remember that phi is equal to B times A. It's actually B dot A. But in this case, the area and the magnetic field are in the same direction, right? So the cosine of that angle is going to be 0 degrees. So I can say that this is equal to BA cosine theta. That's my definition of a dot product. But here, theta is 0 degrees. So this is just equal to B times A. Remember, my area vector, it has a vector that is perpendicular to the surface. And my surface is this half loop. That's the area that I'm concerned with. So that's why I lose that angle theta here, because the angle theta is in the area vector and the magnetic field vectors are both out of the page, and they have an angle equal to 0 degrees. So, coming back here now, the induced EMF is going to be equal to minus the area times dB dt, because my area is constant, but you can envision a loop that actually change the area, and then that would cause an induced EMF as well. And so this is going to be equal to minus the area, which is pi r squared, divided by 2. It's a semicircle, so it's a half loop. So it's the area of a circle divided by 2 times the derivative, ddt, of my magnetic field function. That's 4t squared plus 2t plus 3. And then we can take that derivative, what's that? What is that derivative? Right, 8t plus 2. Remember with our derivatives, we just say the exponent times the coefficient, and then reduce the exponent by 1. So 2 times 4 times t to the 2 minus 1, and 1 times 2 times t to the 1th power, the first, or to the 0th power, which is just 1. So then this works out to be negative pi times 0.2 meters squared divided by 2 times 8 times 10 seconds plus 2. And I find that this is equal to minus 5.2 volts. So my EMF here is minus 5.2 volts. Notice that if I in fact do have a voltage, say of 2 volts, then that means that it's going to interact with these two. So my total EMF would equal to 2 minus 5.2 volts, which would be minus 3.2 volts. So I have a voltage that's provided by the battery, but then I have another voltage that's provided by this changing magnetic field. You have some homework problems that are similar to that, so take a look at them. But you'll probably see a problem something similar to this, where you have a changing magnetic field, maybe one like this, or maybe one like the one that we worked last time, where we had the two coils, one inside the other, and you change the magnetic field. You have to figure out what then is the induced EMF, and then also maybe what is the induced current. So if I wanted to know the induced current, by the way, I could just use Ohm's law and find that I is V over R, which if I have this total of minus 3 over 2 volts divided by 2 ohms, then that would be minus 1.6 amps, which would be clockwise. Okie dokie. We'll see this again a little bit more next time when we come back. But let's look at induced E fields. So we have a changing magnetic field. This is Faraday's law. Produces an electric field. And the electric field has been sort of ever present all along this, because we've been talking about a changing magnetic field, and then we talk about an induced current. But really, it's not the current that we're inducing, it's really the electric field that we're inducing. And then the electric field just generates a current. So a current is caused by an electric field. So Faraday's law showed that a changing magnetic field causes an EMF and hence a current, but really we're really just creating an electric field. Hold on just a second. Actually, let's not do this right now. Let's look at some of the clicker questions first. So I think I have these in the back for you. Am I right about that? Do I have these in the back for this chapter? Okay, well let's do some of these then. Let me pull up your clicker base. Okay, so on this one, I have a square conductor that moves through a uniform magnetic field. And a square conductor, you know, it has charges in it. It has positive and negative charges. And we'll sort of think of them as being both free to move around this conductor. And I want to know, as it moves through this magnetic field, what is going to be the distribution of the charges as it moves through the magnetic field? Now this sort of goes back to chapter 5, when I have these or chapter 5 or 6 are force on particles as they move through a magnetic field. So sort of think back to that. And just imagine a positive particle. What direction would a positive particle feel a force if it moves through a magnetic field in this direction? Well, what this is going to tell us is something about the electric field that's set up as I move through this magnetic field. You have a magnetic field that's out of the page. What is going to be the direction of the forces that these particles will feel? Okay. More have it right than wrong, but a number of you have it, about 5 or 6 of you have it wrong. So ask around to your neighbors and see what they put. Or if they're guessing. Are y'all guessing? Some of you aren't guessing, I know, because many of you have it right. Maybe they're good at guessing, yeah. All right. Let's stop at 135. Okay, good. E is right. Remember, think about our particles that if I have a positive particle moving through this magnetic field, the positive particle moves in this direction with a speed v. The magnetic field is out of the page, so I say v is up, magnetic field is like that, out of the page, and so my force then is in this direction. And so my positive particles are going to move over here, my negative particles are going to move over here. So we can also then think about our electric field, that we have this electric field that is set up within this conductor that will be in that direction. So we get this electric field that separates these charges. Or we can think about it in that way. So E is the right direction. What is the induced current in this circuit? And so what I have here is a coil of wire that is moving through a magnetic field. So this coil of wire is moving in this direction through that magnetic field. What is the induced current, the direction of the induced current in this magnetic field, or in this coil of wire? Okay. What is required for the coil of wire and the magnetic field in order for it to have an induced current? Remember that our induced current is equal to negative d phi dt, and that phi is equal to b dot A. So what is required in order for this to happen regarding our orientation of our magnetic field and our area vectors? In order for this dot product to not be 0, what must be true about B and A? They have to be what? Well, they have to be in the same direction, right? And remember that our area vector is perpendicular to the surface of the area. So in this case, this is my area vector. So my area, or this is my area, so my area vector is actually out of the page at this point, or into the page. So then what is going to be my induced EMF, or my current, in this coil of wire? Okay. Any of you have the right answer? Ask your neighbors what they put, okay? All right. We'll stop at 2:30. 2:30. Okay. It is is no. C is the right answer, because here dA is perpendicular to B. And because of that, B dot A is going to equal to 0. That there will be no current at all in this loop, because the magnetic field, in order to have a current in this loop, would have to be perpendicular to the surface of the loop, which would be in the same direction as the vector dA. Remember our flux measurements, okay? You're going to have to calculate some flux on the next test, just like similar to what we've done before. I want you to tell me, as I'm pulling this coil of wire through this magnetic field, I get changing magnetic fluxes at various places. And I want you to, because of those changing magnetic fluxes, I'll have this induced magnetic flux that will cause a force to act upon the coil. This is just like the magnet dropping down through the copper wire, very similar to it anyway. So I want you to rank the forces F1, 2, 3, and 4 in order of their magnitudes. Which has the strongest force, which has the biggest force. Remember, my force will be dependent upon the rate of change of the magnetic flux. Because my EMF is dependent upon the rate of change of the flux. The higher the EMF, the higher the induced magnetic field, and so my force will be dependent upon that rate of change of the magnetic flux. All right, almost everybody has either A or B, or 1 or 2 here. So one of those, y'all are about evenly split on them. One of those is the right answer. So given those, we can get rid of 3, 4, and 5. Think about what is the ranking of the forces. Where will I have the biggest force? Where will I have the smallest force? All right, let's stop at 2 minutes. Okay, good. Y'all are still sort of evenly split. The answer here is going to be A, because I'm worried about the change in the magnetic flux. And so sort of a common mistake is you say, well, there's no force here. And that would be true, right? Because my magnetic flux is not changing. But similarly, my force over here is also not changing. Or rather, my magnetic flux is not changing. So I'll also have 0 force there. But here in these places, where I'm entering or I'm leaving the magnetic field, that's where I have maximum change in my magnetic flux. And so they'll have a bigger value, and these other two will have a smaller value. I think we'll do this one more thing in the notes, and then we'll drop off for the break. So this is sort of what we've seen already. We've seen this a little bit, but I just want to be clear on this. So let's say that I have a coil of wire. I have a coil of wire like this, and I have a magnetic field that is into the page. This is my magnetic field, and the magnitude of the magnetic field is increasing. Because I have a changing magnetic flux, it's going to cause to have a magnetic field that will be in which direction induced by that coil of wire. Will the induced magnetic field by this coil of wire, will it be into the page, out of the page, left, right? What will it be? The induced magnetic field in that coil of wire. Let's do it as a clicker question. The induced magnetic field, will it be into the page, out of the page, to the right, or to the left? The induced magnetic field due to that coil of wire in the middle of that coil of wire will be what direction? Oh, Okay, awesome. We'll stop at 18. Okay, good. B is right. Remember, your induced magnetic field will always be opposite or in the same direction as the magnetic field that you have present. And because it's increasing, the magnetic field is increasing, it sort of wants to keep the status quo. So the induced magnetic field will be out of the page. So my induced magnetic field will be in that direction. And now I want to know what is the direction of the induced electric field. Well, I can go back to my right-hand rule. Right-hand rule, if I have a current in this direction, it causes a magnetic field to go in that direction. So here in this case, my current is going to go in this direction. So at various places in this, I have an electric field that is in the same direction as that current. So my electric field is in that direction. You get this electric field regardless, but you don't experience it unless you actually measure the current. Now we can look at this also. Let's say that I have or I can just think about this actually. Say if there's not a wire there, same situation. I have a magnetic field that's into the page. The magnetic field is increasing. And then I set up this electric field that's going to be counterclockwise. So I don't have a wire here. This just represents the electric field. And so that electric field will go in this counterclockwise fashion. All right. I think that we will stop there. And that's a pretty good stopping point. And then over the break, we'll revisit some of this next week when we come back after the break. I know that it probably said to it, but we're going to jump pretty quickly into LRC circuits, where we'll see different equations, different kinds of circuits. All right? Go ahead and try the chapter 6 homework over the break if you're able, or today. Just look at those. There's only a few questions. We'll take a look at those. And then I'll see you after the break. Okay? Have a great day. Focus on the homework for this chapter. Your exam will come pretty closely from the homework. Lesson 2, right?